This video looks at Nyquist diagrams as a mapping of the D contour. So far then, we've looked at Nyquist diagrams as a plot of the frequency response characteristics of a system transfer function. But now we're going to look at an alternative view. That is, we're going to consider the Nyquist diagram as a mapping, and the specific mapping we're looking at is a mapping from the S space to the G of S space. Now, doing this is going to allow us to utilize complex variable theory, and that is going to help us with our feedback loop analysis and design, which is where we're going next. So this video is going to introduce the specific mapping needed to give a complete Nyquist diagram. We're going to use something called the D contour. Now you'll notice at the top something we've said. The most important point is that the D contour has got 4 right-hand right-angle turns, and we need to include those. But first then, let's sketch the D contour. So it starts at the bottom of the negative imaginary axis, so I'm going to put it alongside just so you can see. So in essence it comes up the negative imaginary axis, so that's all the values minus j omega, and we'll put an arrow to make sure we get the direction correct. Just before it gets to the origin, it skips round, and you'll see I've used a semicircle to represent this. So it doesn't actually go through the origin, it skips around the origin, and it has these 2 right hand, so I put that, so you've got a right hand, right angle turn. Now the reason I know they're right hand is because if you look at these arrows, you can see, if you imagine yourself walking along the arrows, you turn right in order to stay on this blue line, and you do that twice. Now when you get to the top of the positive imaginary axis, you turn right again. So you'll see again a right angle turn, and you've got to basically use a bit of imagination here, because we're not mathematicians, we're engineers, and you can imagine that you then go all the way round the right half plane. So this dotted line is to indicate that's what you're doing. You're going round the right half plane, and you're coming back to join again at the bottom of the negative imaginary axis. So you'll see we do indeed have 4 right hand right angle turns. I'll list them. You have one here, one here, one here, and one here. Okay, what we've got to do is now consider how we map this contour into the G of S space. Now some properties are linked to this D contour. First of all, the D contour is closed, and therefore the mapping must be closed. A complete Nyquist diagram is going to include negative frequencies as well as positive frequencies, and you'll see that because the D contour had the negative imaginary axis as well as the positive imaginary axis. And similarly, you'll notice the Nyquist diagram has got to be symmetric, because simple properties tell us this, that G of j of j omega is the complex conjugate of G of minus j omega. Here's an example then, so you can see a complete Nyquist diagram. The most important thing are these properties we've just mentioned. It's closed. You can see that it finishes where it starts, because if S finishes where it starts, then G of S has got to finish where it starts. And the other thing that's perhaps obvious is it's symmetric about the real axis. Now, next we need to look at something called conformal mappings. That's a property we're going to use. So what I'm going to do here, first of all, is I'm going to put S space down here, and I'm going to imagine a particular trajectory in S space doing this, and then I'm going to put a corner in. So you can imagine if I'd continued along, I'd have followed that dotted line, but now I'm going to suddenly turn abruptly to the right, and I'm going to turn abruptly to an angle A. And now what we want to do is imagine what happens in G of S space. So G of S, we're following a different sort of curve, but what's going to happen, and this is the interesting thing, is the mapping in the G of S curve will also turn abruptly at the same point. So if I imagine that if this was S equals S1, then this point here is going to be g of S1. So at the corresponding point, your loci in the g of S space has got to turn through the same angle, and the key thing, also in the same sense. You can see here I turned right through A, and you'll see I've got the same down here. I've turned right through A, and that's a conformal mapping, which will always happen as long as the mapping or the function here is analytic, which you can consider will be the case for the transfer functions we are going to be dealing with. So what's the significance of this? Well, the significance is the D contour includes 4 right-hand right-angle turns, and therefore the mapping into the Nyquist diagram has also got to have 4 right-hand right-angle turns, because it's a conformal mapping. So the emphasis here is on 2 properties: right angle, right hand. You're turning to the right, so we've got to be very careful always to note the direction of travel, because if we don't know which direction the loci is going, then we can't make sure that we're turning to the right. Now, a note here: in practice we only need to worry about these right hand right angle turns where omega tends to 0, and you'll see why next. First of all, we're going to ignore the right hand turns as omega tends to infinity. Now, why can we do that? Well, in simple terms, we're going to say that as omega tends to infinity, we're mapping to the origin anyway. And why can we do that? Because real systems are always strictly proper. And because they're strictly proper, it means we've got this property here, m bigger than n, where m is the order of the denominator and n is the order of the numerator. And you'll see, if you do this limit here, the limit as omega goes to infinity, in the denominator we've got a j omega to the m, in the numerator we've got a j omega to the n, but if m is bigger than n, then clearly this goes to the origin. And because the mapping as omega tends to infinity is the origin, we're not going to see the right hand turns anyway, so they don't matter. Okay, so for Nyquist diagrams of real systems, we can ignore the mapping of the part of the D contour which is at infinity, because it maps to the origin. Second observation: we can also ignore the other 2 right-hand turns if the system doesn't have an integrator. Now, why is this? Because if there's no integrators, then as omega tends to 0, so as the D contour follows the bit which goes near to the origin, then the gain is going to be a finite constant. Now, why is that? You'll see here, if we do the limit as omega goes to 0, and we're assuming there's no integrator, so the constant in the denominator is not 0, then the limit we're going to get is this, b of 0 of a of 0, which is a finite number. And therefore, for Nyquist diagrams with no integrator, the mapping for the D contour as omega tends to 0 can be treated as a constant, and thus again the implied right-hand angle turns need not be considered. So when do we need these right-hand turns? Well, we need them when we have integrators. So now what we're going to do is look at the mapping of an integrator, a mapping of 1 over s. So first of all, let's put our D contour back in. I better use red here so it doesn't overlay the loci. So what we've got is something that looks a bit like this. So remember, this picture is illustrative of what's going on, and I mark in my right angled turns at the key point. Now what I've got to do is imagine how this maps to 1 over s. The first thing to note is the phase of 1 over s is the opposite of the phase of s, and also the gains invert. So if I do a mapping of this point here, and remember this is minus j omega, it's going to map to the positive imaginary axis, and it's going to map to a very small value because that's a very large value, so that's going to map to there. If I imagine a value up here which is approaching the origin, that's going to map to a very large value somewhere up here. So you'll see this direction here is going to map to something like this. Okay, so the negative imaginary axis maps to the positive imaginary axis when the mapping is 1 over s. Now, what you'll see next is we've got a right-hand right-angle turn. So that's what we get at the top here. We get a right-hand right-angle turn. Now the next thing you see is that S basically changes in phase by 180 degrees in an anti-clockwise direction, and therefore 1 over S has got to change by 180 degrees in a clockwise direction. So we do that 180 degrees clockwise, and you see we come back down here. And then what we're going to get is another right-hand turn. There it is. Again, put the arrows in to make sure. And then you'll see we're on this bit of the axis for S, and you'll see a small value on the positive imaginary axis is going to map down to a large value on the negative imaginary axis. A large value on the positive imaginary axis is going to map to a small value on the negative imaginary axis. So up we come, and again this will probably skip round, but we don't need to worry too much about that. So there's the mapping of an integrator. But the key thing that you're going to need later on is these right-hand turns at the top and the bottom. Oops, sorry about that. And this skipping around in a clockwise direction. Okay, so a summary. Mapping of an integrator. As omega tends to 0, then the integrator, the gain of the integrator, tends to infinity. The D contour has got two right-hand right-angled turns as omega 0 minus and 0 plus. So that tells you the Nyquist diagram, this is of 1 over S, I'll write that there, must have two right-hand right-angled turns corresponding to those values of omega. S, that is the D contour, moves through 180 degrees anti-clockwise around the origin as omega transits from 0 minus to 0 plus, and therefore the Nyquist diagram of 1 over S must move through 180 degrees clockwise, and with infinite gain obviously, as omega transits from 0 minus to 0 plus. And again a reminder about symmetry. Right, next things that come from conformal mappings. So the previous video noted that closed loop stability seemed to be linked to whether the Nyquist diagram passed with a -1 point on the right or the left, where we're talking in terms of directions of increasing omega. So let's imagine this was our Nyquist diagram. Let's mark our direction of increasing omega. There it is. Now, is the -1 point, clearly marked here, on the right or the left? Well, you can see in this case it's on the right. You look to the right. Okay, so there we are. You look to the right. What about this one? Again, mark the directions of increasing omega, there with the arrow, and you'll say in this case we look to the left. So what we want to do is investigate why this might be. Why did the position of the -1 point on the left or the right seem to be important? So let's first of all consider the -1 point is on the right. So first of all, I'm going to redraw this Nyquist diagram so you can see what's going on. I'll mark my -1 point. There it is. I'll put in a typical Nyquist diagram. There it is. Mark my direction of increasing omega. Now, if I want to get to this -1 point, you'll see what I'm going to have to do is I'm going to have to turn right through an angle theta. Okay, so in order to get to -1, I've got to turn right. Now let's look at my D contour that corresponds to this plot. Okay, so if I put in my D contour, here it is. I'm going to be a bit crude because it's not particularly important. Now, what we've got to do is take the specific point we're interested in, which is here, this point here, and let's say that corresponds to this omega here. So what we've said is if you have a conformal mapping, we've got to turn through the same angle and in the same sense. So what that means is in order to find the value of S that corresponds to -1, we have to turn in the same sense. So there we go, we've turned through an angle theta, and we get to this value of S, which corresponds to G of S equals -1. Now what do you notice? We've had to turn right, and therefore we've turned into the right half plane, and we've said therefore a value of S in the right half plane satisfies G of S equals -1, and therefore you must have a right half plane pole. So if you pass and the -1 point is on the right, it's telling you you've got right half plane poles. Now, just very quickly, let's look at the reverse situation, which is what happens if you pass with the -1 point on the left. So again, we'll do our Nyquist diagram. There it is. And you'll see here what we want to do is turn in order to get to the -1 point. And you'll see in this particular case, we've turned through an angle, shall we say, phi, and here you've turned left. So again, if I do my D contour and see what we get from this. Okay, so here's my crude D contour, and what I've got to do is find a frequency omega, which corresponds to this point here. Okay, and then we've said in order to get to the -1 point, we've turned left. So let's turn left through an angle phi. There it is, and clearly the value of S that you end up with that corresponds to giving you G of S equals -1 is now in the left half plane. I should remind you, I'm being a bit crude here, this blue line is exactly overlying the imaginary axis. So as soon as you turn left, you're in the left half plane. So what we've got is if you have to turn left from the Nyquist to get to -1, it's indicating that you've got left half plane poles. So some conclusions. We've demonstrated that a complete Nyquist diagram is a mapping of the D contour in the S-plane. We've identified key properties such as symmetry about the real axis. There are two right-angle turns in the Nyquist diagram as omega tends to 0 for systems with integrators. And similarly for systems with integrators, there's a 180-degree clockwise rotation as omega transits from 0- to 0+ for each integrator in the system. Now, conformal mappings also indicate that for closed-loop stability, the Nyquist diagram must pass with the -1 point on the left, and that's marked in the direction of increasing frequency.